This is part 6 of the series Integration, and in this section we're going to look at what happens as we increase the number of subintervals for our summations in our approximation of areas of regions under a curve. So the first thing we're going to look at here is the limit of a lower sum and upper sum. If we let f be a continuous and non-negative function on the closed interval a to b, the limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. In other words, the limit as n approaches infinity of the sum from I equals 1 to n of f of little m sub I, that's the lower sum, times the width of the subinterval, equals the same limit with the same sum of the upper sum. And the assumption is that delta x is your upper limit minus your lower limit divided by the number of subintervals. F of little m sub I and f of big M sub I are the minimum and maximum values on that subinterval. If you recall our previous example, the picture showed us that the right endpoint gave us the maximum value and the left endpoint gave us the minimum value in that particular subinterval. So in this subinterval, maximum value, minimum value. So the lower sum is the minimum value, the upper sum, the maximum value. So that's what we're talking about here when we deal with this f of small m and f of big M. Now, this brings us to the definition of area of a region in a plane. If f is continuous and non-negative on the closed interval AB, then we have the area of the region bounded by the graph of some function f, the x-axis, and the vertical lines x equals a and x equals b, that is the lower limit and upper limit of our sums. This is the area of the region under that curve, and it's given by the limit as n approaches infinity, as the number of subintervals approaches infinity from I equals 1 to n of those subs. So f of c sub I being any value within this subinterval, or in any particular subinterval, times the width of each subinterval. And the assumption there again is that c sub I is any x value between the lower and upper limits between this piece and this piece in each subinterval. And of course delta x is always the upper limit minus the lower limit divided by the number of subintervals. Now I wanted to show one more visual so that we make sure that we can get a really firm grasp on this idea of finding the area of the region under a curve. And here is another picture, and this is very similar to what we had before. We have 5 subintervals, and we have a left sum or a lower sum here. So there's the lower sum, and here's the right sum. And if we take a look at these two values up here, we can see that the left sum is lower than the right sum. These are the values that we got from our example in our previous example. If we now increase the number of subintervals from 5 and we increase it, you can see that these numbers are coming closer and closer together. And as we increase this out to some fairly large number, you can see that these numbers become accurate to within a couple of decimal places. And if we were to increase this beyond that level, you would see that these numbers would in fact coincide. And that should be fairly logical, because if you think about it, you can see that this corner is getting closer to the actual curve. So we're actually including a smaller and smaller portion of each rectangle outside of the rectangle in the upper sum, until the point where we get those values are right on the curve itself. So that's the idea behind this, that whether we're using a lower sum or an upper sum, these values, the area that we're taking here, becomes closer and closer to the actual area under the curve as we increase the number of rectangles. So that's the idea of area. And we're going to go ahead and put this into practice. So in this example, we have the function f of x equals x to the third. We're looking for the area of the region bounded by the graph of the function, the x-axis, and the vertical lines x equals 0 and x equals 1. So let's begin. The first thing we're going to do is find our delta x sub I and our x sub I. So first order of business, our delta x sub I. So our delta x sub I is going to be b minus a over n, and we're finding the actual area of the region, so this n is going to stay an n term because we're actually going to be taking the limit of these values, and so it's going to be 1 minus 0 over n, which is just 1 over n. Now our x sub I, that is the x value for our endpoints, for the sake of ease of use, we're going to pick the right endpoints because I don't want to go through all that I minus 1 business. So we have the lower limit, 0, plus our I term times our delta x, the width of each subinterval, which gives us I over n. And so now we have our delta x sub I and our x sub I, and we can form our limit. So we're taking the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x sub I, which gives us the limit as n approaches infinity of the sum of I equals 1 to n of this piece, so it's I over n cubed times delta x sub I, 1 over n. Now, to simplify this out, that's I cubed over n cubed times 1 over n, which gives us I cubed over n to the fourth. And these limits, the sum and the limits follow down, so we have the limit as n approaches infinity for the sum of I equals 1 to n of this term. Again, we have this constant term, so that can come outside, so that's n to the fourth, 1 over n to the fourth times the sum from I equals 1 to n of I cubed. So we'll go ahead and take that sum using our rules, and so this gives us 1 over n to the fourth times, so the sum of I cubed is n squared times n plus 1 squared over 4, and that whole thing times n 1 over n to the fourth. Now I've gone ahead and done the algebra. If you're interested in the algebraic details, you can always pause the video and walk through it. But as we get down to this point, we get to this final term. This would be our term for the approximation of the area under the curve. We take the limit and we get the area. So 1 over 2n goes to 0, 1 over 4n squared goes to 0 as n goes to infinity. So our result is 1/4. So this gives us the exact area under the curve because we took the limit as n approaches infinity, meaning the number of subintervals approaches infinity. So let's go ahead and do another example. In this problem, we have a slightly different situation. Our function is very similar, 4 minus x squared, but our limits to where we're finding the area of the region, we start at 1 and go to 2. So we're no longer going from 0 on. So that's going to factor into our calculation of our x sub I value. So let's go ahead and get started with that. Our delta x sub I is going to be b minus a over n, which is 2 minus 1 over n, which is 1 over n. Then our x sub I is going to be a plus our I value times our delta x, 1 over n, which is 1 plus I over n. And so this is now our x sub I value, 1 plus I over n. We can expand this out, make it n plus I over n, and that may make things a little bit easier for us. Let's go ahead and put in our limit. So our area is going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I. This value goes into our x term, so it's 4 minus n plus I over n squared. That whole thing times our delta x sub I, which is 1 over n. Let's go ahead and work this out. So quickly working through this algebra, I just expanded this quadratic. N squared plus 2ni plus I squared is the top term, n squared is the bottom term. Then I combined these to get a common denominator, simplified, and then I divided each one of these terms by n to the third and got this expression. This is the expression we're going to use to create our sums. So we pull out the n, 1 over n. This is the sum of I equals 1 to n of 3, minus, pull out the 2 over n squared, and that's the sum of I, minus 1 over n cubed times the sum of I squared. Now let's go ahead and take these sums and see what results. So the sum of a constant is the constant times n, so 3n, minus the sum of I is n times n plus 1 over 2, so that's this quantity, minus the sum of I squared is n times n plus 1 times 2n plus 1 over 6. Now we simplify this, n over n is 3, minus this simplifies to this, n squared plus n divided by n squared, and the 2's canceled out here, minus 1/6, we pull that out, and this top term becomes 2n cubed minus 3n squared plus n. If you multiply this out, you get that, divided by n cubed. Then here we simplified, n squared divided by n squared is 1, n divided by n squared is 1 over n, and 2n to the third over n to the third is 2 plus 3 over n plus 1 over n squared. Now when I take the limit as n approaches infinity, this term goes to 0, this term goes to 0, and this term goes to 0. So we have 3 minus 1 minus 1/6 times 2, which is just 1/3. 3 minus 1 minus 1/3 is simply 5/3. I would recommend, if you're weak with the algebra, work through these problems again just to get comfortable with it. These are excellent practice on algebraic manipulation, and work through the idea of forming your delta x sub I and your x sub I, and you shouldn't have any problem. Let's go forward and do one more example before we move on to the next topic.